Hello friends, and in this video, let us discuss about depth first search DFS. So we have learned about graphs and how can we traverse graphs, that is, visit every node of the graph. We have two major methods for that. One is breadth first search BFS and the next one is depth first search DFS. We have already learned about BFS, which uses a queue. And in this video, let us discuss about DFS, which uses a stack. Simply, let us understand how it is done. Let us start from vertex A. So visit A, insert it into the stack and add it to a visited array also. In this array visited, the vertices that are visited will be added. Now it has A only. It means only A is visited. Now take A from stack and push its adjacent nodes into the stack, that is B, C and D. So these are pushed into the stack and added to the visited array also. Now pop the element from stack, which will be the top element, which is D here, and visit its neighbors, which are A, B, C and E. A, B, C are already visited. So add E into the stack and visited array. So E is pushed and inserted to the array also. Now again pop the element from stack, which is E. Now visit all neighbors of E, which are B and D. But both are already visited here, so do nothing and pop the next element, which is C. And again, all the neighbors of C are already visited. So pop again and we got B now and its neighbors are A, D and E. Again, all these are visited. And now the stack is empty and there are no more nodes to process. So we can say all nodes of the graph are visited now. So this is what DFS traversal is. We start from a vertex node, visit it, visit all its neighbors and then choose one vertex from it, then visit all its neighbors and continue. So let us see how to implement it. First, let us define the size of stack as 25. Next, we have some functions. We have the eStack full function here to check whether the stack is full or not. If the stack is full, this function returns 1, else it returns 0. We have if top equal to size minus 1, return 1, else return 0. Next, we have the push function to perform insertion into the stack. When this function is called by passing an element, it will be inserted at the top of the stack. Next, we have the eStackEmpty function here to check whether the stack is empty or not. If the stack is empty, this function returns 1, else it returns 0. We have if top equal to minus 1, return 1, else return 0. Next, we have the pop function which performs deletion from the stack. When this function is called, the element at the top of the stack will be deleted. But defining all these functions is difficult and makes the program very lengthy. Instead, we can simply include the stack.h file which has inbuilt functions for stack operations. So we include stack.h and define size of graph V as 5. Now in main, let us define the graph as an adjacency matrix. So we have ARR of VV equal to these values. So the graph is defined now. Now let us call the function DFS by passing this adjacency matrix ARR and the starting vertex. We can start from any vertex. Here, we will start from the vertex 0. So control gets here and ARR is stored in ARR and 0 is stored in source. And as we know, for DFS, we need two data structures, a stack and a visited array. So declare the array is visited of size V, that is 5, and initialize to 0. Now declare another integer variable index. Now the first step is to insert the starting vertex to stack and make it visited. So write push of source. So 0 is inserted into the stack. Now make it visited in the isVisited array. So isVisited of source, that is isVisited of 0, is equal to 1. Now we have to visit its neighbors. For that, we can use a while loop till the stack becomes empty. First, remove the element from stack and store it in node. So 0 is popped and stored in node. And now print 0 is visited. Now how can you find its neighbors? See, this is vertex 0. If there is an edge from 0 to 1, 1 is a neighbor of 0, and if there is an edge from 0 to 2, 2 is a neighbor of 0, and again if there is an edge from 0 to 3, 3 is a neighbor, and it will continue like that. And how can we check that here? We can simply check the adjacency matrix. Which all columns are having value 1 in 0th row? We have 0, 1 equal to 1, 0, 2 equal to 1, 0, 3 equal to 1. So 1, 2 and 3 are neighbors of 0. So this is the logic. So use a for loop for index equal to 0, index less than v, index plus plus. In first iteration, index is equal to 0. Next we have if ARR of node index equal to 1. That is, we are checking whether index is a neighbor of node or not. And is visited of index equal to 0. That is, checking if it is already visited. So if index is a neighbor of node and if it is not already visited, we have to add it to the stack and make it visited. But here we have ARR of 0, 0 equal to 0. So if fails, and in next iteration index equal to 1. And ARR of 0, 1 is equal to 1 and is visited of 1 equal to 0. That is, 1 is not visited yet and it is a neighbor of 0. So insert it into the stack and make it visited. So is visited of 1 equal to 1 now. Now in the next iteration, index is equal to 2 and ARR of 0, 2 equal to 1 and is visited of 2 is equal to 0. That is, 2 is a neighbor of 0 and it is not visited yet. So insert it into the stack and make it visited. So is visited of 2 is equal to 1 now. Now in the next iteration, index is equal to 3 and ARR of 0, 3 equal to 1 and is visited of 3 is equal to 0. That is, 3 is not visited yet and it is a neighbor of 0. So insert it into the stack and make it visited. So is visited of 3 is equal to 1 now. Now in the next iteration, index is equal to 4 and ARR of 0, 4 is equal to 0 and not 1. So if fails, and in next iteration index is equal to 5 which is not less than v. So condition fails and control comes out of for loop. Now in next iteration of while loop, we have to remove the element from the stack and store it in node. And 3 is the element at the top of the stack, so it is popped and stored in node. Now print vertex 3 is visited. Now we have to visit its neighbors. So again use the for loop. In first iteration, index is equal to 0 and ARR of 3, 0 equal to 1. That condition is okay, but is visited of 0 is also equal to 1 and not equal to 0. That is, 0 is a neighbor of 3 but it is already visited. So if fails and in next iteration index is equal to 1 and ARR of 3, 1 is equal to 1 but is visited of 1 is also equal to 1 and not equal to 0. So again if fails here, in next iteration index is equal to 2 and ARR of 3, 2 is equal to 1 but is visited of 2 is also equal to 1 and not equal to 0. So again if fails and in next iteration index equal to 3. And ARR of 3, 3 is equal to 0. So if fails again. And in next iteration, index is equal to 4 and ARR of 3, 4 equal to 1. And is visited of 4 is equal to 0. That is, 4 is a neighbor of 3 and it is not visited yet. So insert it into the stack and make it visited. So is visited of 4 is equal to 1 now. In next iteration, condition index less than v fails and control comes out of for loop. And in the next iteration of while loop, stack is not empty yet, so continue. Perform pop operation to remove the element at the top and store it in the node. So 4 is popped and stored in node. Now print 4 is visited. And now we have to visit its neighbors. But if will fail in every iteration of this for loop, since is visited is 1 for every index. And in next iteration of while loop, pop the element from stack which will be 2 and print visited node is 2 and again the same happens. and in next iteration, pop the element from stack which is 1 now and print visited node is 1 and again the same happens. And in the next iteration of while loop, the condition not is stack empty will fail since the stack is empty now. So control comes out of while loop and the traversal is now completed. Now one question to you. Why did we use the isVisited array? And what will happen if we didn't use it? See, a traversal means we have to visit each node. If we hadn't kept track of visited nodes, we would visit it again and again. And we know graphs might contain cycles and we might get into an infinite loop. So using this Boolean array isVisited, we can avoid such issues. So this is what depth first search traversal is.